Hi, in this video, I want to introduce the first unit of Medical Instrumentation 2. And in the first few lectures, we are going to look at digital systems. And what I want to do in this particular lecture is just try to introduce digital systems to you, what they are, and why they are important, and what are we going to study about digital systems in this particular unit. So think back to what we have already studied as a part of Medical Instrumentation 1. Okay, what we have already looked at is how we design analog circuits. So let's assume that we want to design a system. Okay, let's just make it a black box here. And the system has an input V in and an output V out. And I tell you the relationship between the input and output that I want you to get. So I say V out needs to be 50 times V in minus 320 millivolts. So how are you going to go about designing that circuit? The way you would do it is you would say, okay, I know how to make a circuit that subtracts 320 millivolts. So that would be my step one. And then I know how to a circuit which multiplies by 50. So that's step two. And then I put both these circuits together, and I have my circuit which goes instead of this black box, right? So of course, if you remember analog electronics, you would remember that the first circuit is made by what is called a differential amplifier. And what we can do is, let me just draw that. So I put a resistor here and a resistor to ground here. Let's say I give V in at this point, and I create a similar circuit but with a, so that's all these resistors are R. I give 320 millivolts here. So the output that I get here is going to be V in minus 320 millivolts. And then I basically make an inverting amplifier. So there you go. So that's the out that we wanted, and this would be connected to ground. Okay, so a fairly straightforward way of doing circuit design. But now let me ask you and say, okay, I'm going to change the relationship a bit and say I want V out equal to 50 times V in square minus 320 millivolts. And now all of a sudden what you need is a circuit that can do a squaring operation. And perhaps you know a circuit that can do a squaring operation and you can put it in. But what would you have to do to the previous circuit? You would have to kind of redesign it altogether, right? You would have to put one more component in the circuit so that we can get a square of a signal. Let me make it a little bit more complicated and say what I want is 50 times e to the power v in minus 320 millivolts. Now things are starting to become more and more difficult, right? So as I keep changing the signal conditioning that I want, or the input and output relationship that I want, what you see is you have to almost entirely redesign your circuit. Uh, and this is where I say, if I had a device which could be programmable. So what do I mean by that? What I mean is that instead of changing the hardware, changing the number of chips that are there in the circuit, I could program something into it and program a mathematical operator into the device. That would make things very easy, wouldn't it? So let me just draw a block diagram to explain what I'm talking about. So think about this device here, and this is a programmable device. I give it a V in and I take a V out, and I say whatever mathematical operation that I want. So V out is a function of V in. So this mathematical operation, you don't need to change the circuit, but what you need to do is you want to program it into this hardware, which is already present. So what this does for you is that the hardware becomes uh, constant. It doesn't need to be changed, and all that needs to be changed is the software. Now this has two advantages. Firstly, it enables us to get very complicated functions into the device. So complex functions, or let's put it, the advantage as complexity. You can have a lot of complexity built in into the kind of transformations that you can do with this device. The second thing that it would help you with is cost. Sure enough, the cost of the hardware here, that is implementing the programmable device, may be much more than the cost of uh, the simple analog electronic device that you made before. But if you take the overall cost, and what does the overall cost consist of? It would consist of the designer's time, and also it would be determined by how many units of this circuit you are selling, right? So if this circuit is a very general purpose device that can program a lot of different functions, then you can send millions of these devices compared to a very few of the devices that we programmed before, which cannot really be customized very much. And therefore that reduces the cost, right? In addition, of course, the developer cost is much less in this particular case. Why? Because all you need to do is program. And programming is much more easier than analog circuit design, especially for complex circuits. So the cost is also reduced. So all this to kind of help you see why, if we could have a programmable device, that would be very nice. But how do we get that? How can we get a device that is programmable? And how can we um, actually get this implemented? So here's a solution. So let's say we have a sensor, and it is giving you an analog input. Okay, you do some very simple signal conditioning right at the starting, something that wouldn't take much of a time to design. Okay, let me write it as signal conditioning, and then give this signal to a ADC, or an analog to digital converter. So this converts the analog value into a digital value, and then this digital value is given to a programmable logic. And I'm just, for simplicity, let me call it a computer. Okay, so you're familiar that computers can be programmed. So let's say we give it to a computer, and the computer actually does the computation that is involved, the transformation that is involved. And then the computer, if required, can send the digital value, the digital output, to a DAC, which does a digital to analog conversion. So it does the opposite function of what the ADC did. So it does a digital to analog conversion, and at the output here you have an analog output. Okay, so this is kind of the summary of the digital systems that we are looking at in this particular lecture or in this particular unit. Okay. What we are going to be doing is we are going to be learning about how we can program, and of course we are not going to look at computer programming. Instead, we are going to be looking at a special class of computers, you could call it computers, called microcontrollers. These are basically small computers along with some additional devices that help us um, to do this processing. So for example, the microcontrollers usually have an inbuilt ADC, so you don't need a separate ADC, so it has a peripheral attached to it, and we'll just study how we can program this microcontroller. So that is programming. So that's the first part of our digital systems unit. Um, and then what we're going to look at is we'll combine ADC and DACs and look at it and call them data conversion. And we'll look at data conversion, the theory behind it, in the second part of our lecture. And then in the last lecture, what we're going to do is we're going to look at this entire system. And then we're going to say, okay, how do we actually process analog signals using digital systems? Okay, and we will call that digital processing. So that's the plan for this particular unit. We're looking at microcontroller programming first, then we'll look at data conversion, and then we'll look at digital processing. And hopefully, by the end of this particular unit, these 3 lectures that we'll have, you will be able to have a flavor of what goes into designing digital systems. Great. So let's carry on and we'll start looking at microcontroller programming in our next video.